Hi everyone, I'm very happy to welcome you to the Learning Journey Hazard and Risk Assessment. My name is Tony Jör. I am working as a DRR advisor with the Swiss Red Cross, and I am also a member of the core group of the Swiss NGO DRR platform. As always, just before to start with, a few etiquette remarks for this webinar. We are recording as from now. Nora, is that right?
Yes.
Okay, thanks. We do that for all sessions in plenary and we'll upload it on the platform website afterwards. Please keep your mic muted, but you are invited and encouraged to keep your camera on at all times. We are not that many, so it feels better for those who see the screen and see the people joining. You can also ask questions either by raising your hand and using the mic or by using the chat. As always, just some quick words about the Swiss NGO DRR platform. We are today a network of 20 organizations, and our aim is to foster a common understanding on how to best integrate disaster risk reduction and climate change adaptation into programs and projects, and ultimately to increase the resilience of the communities we work with. This learning journey is part of capacity strengthening as one of 3 working areas of the platform. Providing conceptual support and engaging in advocacy and policy dialogue are our other 2 working areas. And we receive a financial contribution of the Swiss Agency for Development and Cooperation, including for this learning journey. And the webinar today is the second module of the learning journey. The learning journey consists of 2 parts. The first part focuses on hazard assessment and has the objective to enhance our capacity as practitioners so we can independently conduct a hazard assessment and know how to retrieve airborne data. This first part consists of 5 webinars that take place from March to May. The second part today focuses on acquisition of satellite-based data. Oh no, the second part, yeah, of course, the second module, but the second part then of this learning journey focuses on risk assessment and cost-benefit analysis. And we have planned also to have 3 webinars and to do that in the beginning of 24. I have to unshare my screen. And let me now introduce you to Andrea Blindenbacher. Andrea is the resource person of today's webinar. She has a Master of Science in Geographic Information Systems and Remote Sensing and has extensive experience in aerial data acquisition, processing, and analyzing. It's just what we need today. Please, Andrea, you have the floor.
Hi, everyone, and welcome to this second session in the learning journey. Does everyone see my slides? Is it sharing properly?
Yes.
I see them. Yeah.
Okay, perfect. Thank you. Okay. Well, today, as Tony introduced already, we'll be talking about the basic data, GIS, remote sensing, satellite imagery, etc., everything that we sort of need to do hazard and risk assessments. Maybe a quick recap why hazard and risk assessment is important in the disaster risk reduction domain. Hazard and risk assessment, especially when using GIS and remote sensing tools, can help to analyze the type of hazards and evaluate the connected risks. It can visualize the risks to communicate them in a better way. Communicated risks hopefully become managed risks over time, which reduces the risk for humans, animals, and the environment they live in. In our case, one would hope to convince people not to build houses, for example, or live in high-risk areas. or convince the government to stop forest logging activities in areas that, when destabilized, as in the nature being destabilized, endangers people. 4 weeks ago, we looked at hazard maps and talked about the classification of severeness of events like landslides, rock slides, debris flows, etc. We concluded that besides the amount of population affected, economic downturn, etc., that mainly the frequency and the intensity play a role, where these two factors depend again on the environmental properties of a certain region. These properties can be captured in data layers. And we did a similar exercise last time already, but I thought since it's been 4 weeks ago already, we should maybe use this again to relate and bring back again what we talked about last time. So like that will be, Nora will create groups, and I'll share the link now in the chat, and it's best if you open this link first on your laptops. Let me know if you shouldn't get access or not being able to edit. It technically should work. Okay, and once in those 5 groups or multiple groups, you can all then try to answer the question, what type of data layers may have contributed to this flood hazard map that we see here. Okay, and we'll have 5 minutes time or so. Everyone's back. Perfect. Good. Well done, everyone. I see some people still have some ideas and throw them in. I see settlement group 1 found settlement shape files, Google map photo, multi-criteria analysis, so that goes already far. We have satellite imagery, housing data, hydrological map and data, order photo, river flow. Yes, very good. I hope it helped a bit to bring back what we've been discussing last time. And yes, these properties can be vegetation cover, as you mentioned, soil type, steepness of the terrain, vegetation amount, discharge in the catchment area, and size of the catchment area, and of course, previously registered events, so historical data. As just demonstrated, all these factors are recognizable here on this background image, and some are more prominent, visible, and others less, because they were just part of the analysis and contribute to this final output. But ultimately, we need tools to combine all these different layers of information. So in this is exactly what we'll be looking at today. In the first hour, I would like to go through some GIS and remote sensing basics. And the goal is to get familiar with different terms you might encounter when going around this domain, when you search for help or on the internet, etc. In the second hour, we look more specifically at aerial data types and options of outputs one can generate this way. Data analysis, combining all the layers of information that are geo-referenced. So this is one of the most important points and makes it all spatial, is that each data layer and each data point has a location on Earth. And to create and visualize conclusive output, this is called the analysis. So we have here, for example, so the different layers of data sources are combined. Here we have street data, buildings data, vegetation data, and then the integrated data layer. In our case, like we've seen before, we work with elevation and slope data, vegetation, silent witnesses could also be data layers, populated areas, historical data, and more. But then more specifically, we'll be using algorithms to filter the data and weigh certain layers more than others, depending on the influence they have on that specific event. And then we integrate those layers into a map where we visualize the output. And the tools to create those outputs are also called spatial analysis tools, no matter in which GIS software or other type of tools you're looking for. But first of all, the hardest part is to get all that data. And we have different data sources. Back in time, a geographer would go out and collect these type of data by hand to later draw up an analysis. And still today, there are phases during such an analysis where some fieldwork doesn't hurt. Like we also going to have potentially a field day where we go see silent witnesses, and finding them is not always easy from aerial data or other type of data. So going out in the field is unavoidable. Today, though, we have many more methods to gather data and can especially make use of all the available technology out there. Let's start furthest away, so all the way here. Furthest away from the Earth's surface in space. There we find a multitude of satellites, all with the task to observe or relay information down to Earth. Useful for our purpose are the satellites that gather meteorological data, like we have seen with Georg during the last module, the Augur system. The precipitation data used in the Augur system also comes from weather satellites like GOES, like we see here. Or then satellites that record imagery with different types of cameras and sensors, like Landsat satellites or other imaging technologies providers, or the most common. Technically, there are only 4 providers of satellite imagery, which are Maxar Technology, Planet, UP42, Airbus Defence and Space. But we'll talk about this a bit more in detail in the second hour of this session. Then there are, of course, the global navigation satellite systems. Voila. Well, where many of us know them more as GPS. GNSS just entails GPS, GLONASS, Beidou, and Galileo, which are the European, Chinese, Russian, and US systems. And the Galileo one is technically working, but is still not available for use. All networks of these are geostationary satellites that send their location down to Earth via radio link. A receiver on Earth's surface can triangulate from this information then its own position by receiving more than 3 of such signals. This is useful for our hazard maps if we need location information on certain events, or now I'm mentioning again the silent witnesses. So if there is a giant boulder that we found that clearly is one of them, we can go there and record its exact location to then be able to place it on a visual map. Then moving a bit closer to Earth, we have aircraft, drones, and cars and humans that can carry cameras and other types of sensors to collect information. Measuring stations here on Earth are often set up in a network that allows them to interpolate values between the different measuring points. This is, for example, the case with meteorological information or also seismic information. And then, of course, we have statistical information on the population, animal species, which type of plants, health indicators, etc. Once collected, a GIS can read all these layers of information, and different types of tools can be used to merge, dissolve, aggregate, and run statistics. Here are some examples of GIS systems. GIS is a geographic information system, and it's a computer system for capturing, or a software for capturing, storing, checking, and displaying data related to positions on Earth's surface. common ones are the open source QGIS. So you pay nothing, and it's a bit more cryptic to understand at times, but there's a lot of data or forums with tutorials and areas where one can ask questions around, so one can dig its way through. Then the biggest commercial one would definitely be ArcGIS by the company ESRI or Esri, US-based, and Global Mapper. These are all very general GIS systems, means they can be used for anything and everything. Where today, though, there are many out there that are specialized, for example, for mining applications or urban planning applications, etc. Oftentimes, these specialized GISs even use parts or code of these big ones in order to, well, just provide features related to that one topic they're in. Anyone have any questions so far? Nora, do you see any, or are we good?
Oh,
Good.
does not have any question.
Thank you. So raster and vector data. Now we're diving a bit more into the different data types. One important concept are that there are these two types of data, raster and vector data. Vector data provides a way to represent real features or real-world features within the GIS environment. A feature is anything you can see on the landscape. Imagine looking down from an airplane or a mountain. You can see houses, roads, trees, rivers, and so on. Each one of these objects will be a feature when we represent them in a GIS application. Vector features have attributes, which consist of text or numerical information that describe the feature. For example, it could be the color or if it's a building, the amount of stories that building has. A vector feature has its shape represented by a geometry. As you can see here, we have points, lines, and polygons. Of course, the points, that could be trees or anything that sticks out. Maybe trees are not the best. This is clearly not the normal way trees grow, but could be just single point features. Or then a road. It's usually represented by lines and multiple vertices that are connected, or polygons, which then represent a surface. A vertex, so each one of those blue points you see there has a X and Y coordinate, and often also a Z, which is the height. And then we have, of course, raster data. And that's data packed in a regular grid, like you can see here. Or it could be an image, like you take almost every day with your camera. That's every time. That's basically some raster data that you're collecting. And each cell, also called pixel, so each square or cell, or also called pixel, has 3 values if it's an image that we recognize with the human eye, and that's usually red, green, and blue. Which also means that if you heard it already, that's the abbreviation RGB, red, green, and blue. This is what our eyes are working in. We'll see and hear that a couple more times. But in such raster data, other information could be represented, like the height in each cell has an elevation, like the height, for example, each cell could be assigned an elevation instead of a color value. It could also be an amount of rain on each cell that falls on each cell. The advantages of rasters are they're more human eye friendly. You don't need to understand what the line or the point or the polygon means in order to understand what the feature is it's representing. Disadvantages of raster data are clearly that features are not available. So if this yellow patch here represents a building, I wouldn't be able to just click on this area here and it tells me it's a building. It will tell me, okay, this pixel has a, yeah, this and this RGB value, for example, but it wouldn't, and maybe all the yellow pixels around it have the same type of RGB values, but it will not tell me that all of them together represent a building. Hence, also a raster data cannot have any attribute data. So you wouldn't be saying, this is a building with 3 stories. That's not possible. For that, we need to convert basically the raster data into polygon-based data and then assign the attribute data to that feature layer. And that's exactly what happens. In order to make the most out of both worlds, vector and raster data, they are often combined. For example, here we see a vector data layer and placed on top or under, there could be the raster data. Here we can see that there is clearly an image below features like a road and other points of interests, which are vector data based. Or then, or raster data is used to extract feature data by means of manual vectorizing or computer-aided algorithms like image segmentation, which we see up there. When we're segmenting an image, it's just divided into area of similar looking parts of the image, but it's not yet labeled. Then we could classify it into like buildings and roads. Those tools exist. Or what we hear more and more is artificial intelligence and deep learning, where it's a bit small here, but here, for example, the algorithm identified all the cars on that image. Now I want to show you an example of OpenStreetMap. You probably have heard of it already or, well, encountered it in one or the other way. OpenStreetMap, also called OSM. It's a community-based mapping initiative and is very valuable, especially in areas of less interest to the commercial capitalized world. Anyone can create an account and help map by vectorizing buildings, roads, land cover, etc., based on a given satellite image. It's a little video. So you can see the little hand there moving and vectorizing that building. Now it's going to the left and assigning it the label building. Sorry, it's in German. My browser didn't want to cooperate with the English. Voilà. And it's confirmed. Now this is labeled as a building. Now it's doing another one. It's another building. You can see someone had also gone in and mapped out all the roads that we can see there. Little side note to that, there is HOT OSM, which is the humanitarian OpenStreetMap team. They're basically building projects. They have a website. You can go in and you see they have a project, for example, for the earthquake in Turkey or in Syria, or cyclone in, what was that, in Malawi. And they're basically looking for people to help map or vectorize those areas, whatever is missing at that time. Oftentimes, Google would not go into these areas to map them because they're economically not interesting enough. But yeah, anyone can participate, and you may have also seen, here we see the little logo of Missing Maps. They are organizing so-called mapathons where people meet up in a place, they have some pizza, they all brought their laptops. They make sure they have internet and they map one of those projects, do the best they can. Of course, it's not always easy to recognize what a feature is. which brings us to the next topic. So if we zoom into this area here, you can see it's quite hard to recognize what exactly the outline of the buildings are now in this case, but there could also be other types of features that are hard to recognize. And that's because we have zoomed in further than the actual resolution of the satellite image provided. This is why the image becomes blurry. To be more precise, we would need a higher resolution aerial image. And this brings us to the next topic. But before that, do you have any questions regarding the difference between raster and vector data? If not, then we keep moving. So resolution, it's too low resolution means basically not enough information per raster cell that we could do something with it. It's the detail that is visible it's what we can basically recognize or not recognize depending on that type of resolution. You can see on the left side, we have a low resolution image where we can barely recognize the road and the buildings. And on the right side, we have high resolution imagery where we can well recognize even the palm trees and the little bushes. It's often the case that publicly available aerial imagery, especially from satellites, is quite low resolution, means they're not very good and will not provide enough detail to do proper mapping. So one would have to go and invest either money or other resources into getting a higher resolution imagery. Resolution depends on the distance between the sensor and the Earth's surface, and of course the quality of the camera. Where you hear already there are cost implications coming into the picture. Rule of thumb is that we need around 3 pixels to detect an object, so just to recognize that there is something, and we need around 6 pixels to recognize it, to be able to say, okay, this is a car. Before it was maybe a bit with 3 pixels, with 2 to 3 pixels may have been a bit blurry, so yes, there is something, it could be a car, but we are not sure. And with 5 to 6 pixels, we know, okay, it's a car. So resolution.
Can I ask
yeah.
Could I ask a question to the slide before?
Yeah.
When you look at those different resolutions, you know, the low one, would that be just the normal, you know, the normal one that we could get from satellites, and the other one would be a military one or something in between? It just a bit to understand, you know, on this quality aspect.
Definitely. Which actually also brings me to the next slide.
Okay, good.
Perfect. So what you've seen there is maybe a satellite with the low resolution image was maybe at a 10 meter or more meter per pixel covered satellite image. So it means 1 pixel, one of those raster cells covers more than 10 meters on the ground, which means it's very low resolution. For example, a car is not 10 meters long. In a pixel that is 10 by 10 meters, you don't recognize that car. It disappears in the blur of the information within all these 100 square meters in that case. Satellite imagery can be acquired from around 0.3 meters or 30 centimeters up to 10 meters or more. Then from aircraft, one can receive very high resolution, like 5 centimeters up to 25 centimeters. And from drones, even higher, down to 1.5 centimeters to 5. Yeah, 50 is already, I forgot the 0 there. But of course, you can always downsample basically an image. If you got a 5 centimeter per pixel image, you can always make it a 10 or 20 or 30 centimeter per pixel image. Of course, you're losing then all that information that you had in the 5 centimeter one, but that's always an option. I'm saying this, one would think, oh, who would do that? But I'm saying this because the higher the resolution of the image, usually the bigger the amount of data you're having to deal with. So at some stage, if the computer cannot handle it anymore, you might decide, okay, I'll have to work with a lower resolution just because, yeah, I'm limited on work, like memory power on my computer. Tony, did I answer your question more or less?
Well, yeah, you know, when I look at the satellite, 30 centimeter pixel, that's not for free, I would now assume. Huh?
Yeah.
That's costly.
Yeah, so we get to that in the second part in more detail, but yes, the higher the resolution and the better the data quality you want or you need, the more you pay ultimately. Still satellite imagery, you'd be around 100. Yeah, it varies a lot. Huh? So, but you might be paying like $100 for a good resolution or down to a 30 centimeters image per square kilometers. Where with aircraft, you would be around $400 per square kilometer of a 5 to 10 centimeter per pixel raster. And with drones, gets cheaper again. You might be around 50, no, yeah, 50, yeah, 50 $50 per square kilometers. However, the drone cannot cover such large areas in one flight. So we will talk about it more, but there are advantages and disadvantages to each of these different data sources.
Andrea,
yeah.
Can I just interrupt for a moment regarding this this topic? For some organizations, there are agreements, for example, with Airbus Defence and Space. IFRC, for example, receives for free satellite images with a resolution of 1 meter. Not for the whole world, always for a specific area, but you can choose this area, inform Airbus, and they will provide you those data, but depending if you have those agreements.
Yeah, I was going to mention that as well. And in the second session there, I also know that the company Planet that we saw before on one of the slides has also agreements with humanitarian organizations to have satellite imagery available in case of disaster for very few money or very little money, or for or have other types of contracts available. So it's a matter of reaching out. Maybe yours has already, but this can definitely be explored, and there are other humanitarian organizations that do it already. So I assume this should be something that is organizable. Any other questions on this specific topic? As I said, we go back to it a bit more again as well. And of course, with at least my next course or session, session number 4, where we talk about the use of drones, we'll definitely dive even more into what drones can do or cannot do for you in these type of circumstances. With resolution, there also comes the map scale. If you order any aerial imagery, you must know the resolution or the map scale you are looking for, besides the location and the extent. The map scale is often the more critical measure if it comes to printing printout maps. In digital outputs, the resolution of the data defines the maximum scale to which one basically can zoom in to see the data properly, or to which level the data is still readable. The map scale, like here on the Swiss topographic map of Langnau, The scale is stated at the top with 1 to 25,000, which means that one map unit represents 25,000 units in reality. There was a guy, Waldo Tobler, a renowned cartographer, established the following rule, and that is dividing the denominator, so the 25,000 in this case, of the map scale by 1,000 to get the detectable size in meters, 25 meters. So anything that's 25 meters large can be detected. If now we want to go down to the required raster resolution, we'll have to divide the 25 again by 2, which brings us to 12.5 meters for that specific raster resolution that we would need in order to create this type of scale map. Of course, this also works the opposite way. So going from raster resolution to the map scale, you just turn around this entire calculation and you know what you can end up with if you use 5 centimeter resolution raster or so. It's not super important, but for our purposes, I think for the moment, but I thought I put it in there anyhow for making this complete. The next very important topic is, of course, the coordinate systems. Be it raster or vector data, all the information needs to be geo-referenced for it to be useful in a GIS analysis or spatial analysis. Georeference means that all the data has attributes defining its location, so-called coordinates. There is another type of information that defines something's location, and that's the address. And there are special tools to convert or bring in addresses, etc., and then end up with a coordinate value for this type of object and vice versa. Only with these coordinates, we can then measure distances on the surfaces that reflect the reality. Unfortunately, some bad news, and you can see already here, this image here, there are many different types of coordinate systems, where coordinate systems are just reference systems. So everyone decides, often in each country, etc., they decide on what is most useful for them. And it's a way to ensure that all data within one project is based on the same level. Right? We are not talking apples and pears, but only apples. Each system is a mathematical model of the Earth's surface, often adapted to a smaller region. Since the Earth is very irregular, unfortunately not as nice and round as we see it here on the left side, it's very irregular, so that one model wouldn't fit all of the globe and therefore not make up for the required accuracy. There are global coordinate reference systems. However, those are too generalized and therefore are not used, for example, for construction purposes or landowner boundaries, since they're just, they're not accurate enough. If you take a coordinate like that, you might end up, and like you put it on your phone and you walk to this location, then you'd end up 2 or 5 meters away from that place. That would be just a horizontal shift, but it's usually even worse in the vertical shift. And you can imagine that, if you build a house using that type of data, it's probably not going to look very pretty. This brings us also to vertical coordinate systems, because they're not only X and Y or horizontal coordinate systems, there are also vertical ones, which is exactly the same things. One has to decide on a common reference level for the height. It is not straightforward to determine the center of the Earth or a common surface level, since oceans and terrestrial surfaces depend on gravitational activities inside the Earth's mantle, as well as on moon cycles. There are height models adapted to a specific region or country and generalized ones for the globe. Here is a little example of why it is important to make sure that in one project, everyone uses the same vertical coordinate system. This is near Basel in Rheinfelden. They built a bridge crossing the Rhine, so going across the country border from Germany to Switzerland. When the bridge was built, the German construction company started on their side and the Swiss one on the other side. Once they got closer to joining in the middle, they noticed that they were not at the same height. What happened? Well, the German company used its vertical coordinate system, which is based or referenced to the North Sea, so up here. And Switzerland used theirs, which is the rock in the Lac Le Mans, so in the Genfer See. And this, of course, caused a difference of 54 centimeters. So they found ways, but they had to fix this problem. So, yes. But in order not to make it too complicated for you, there is a site where you can look up all the coordinate systems. Each system has basically a code, a so-called EPSG code. If you don't know the code in a certain region, etc., don't hesitate to ask a local what they're usually working with, either a GIS person or a surveyor or someone who works with coordinates, or then just stick to a UTM zone, a universal transverse Mercator. It's one of the most common that we know and basically also see every day whenever we open Google Maps or any other web maps. It's Web Mercator there, but it's very similar. And that one, it's a good coordinate system, but it has its flaws. We didn't go into details why there are different shapes here, but of course, some coordinate system would preserve certain properties more than others, etc. But the best is to always stick to one. UTM zones is not bad if one doesn't go build a house. If we need it more general, then that will work. And on the vertical side, WGS 84, it is a global vertical coordinate system, but it is practical since any data that comes in via a GNSS receiver, or also called GPS, if you're more familiar with that, you can use those coordinates directly and don't need to transform them. Now I use the word transforming. Any GIS software will provide you with a tool called coordinate transformation, and you can throw in, it usually recognizes what the coordinate system of that data is that you put it in, and then you tell it to what you want it transformed to, and it will do so for you. Oftentimes, if you open any GIS project or a spatial project, even if it's not in a specific GIS software, it will require you to set the coordinate system used for that project. And then some of this software can even transfer or transform data on the fly. So as soon as you put it in, it recognizes, oh, it's not the same, it transforms it automatically. But just double check, it's always in what you want it to be. So since that is a complicated topic, 4 options for you. Stick to WGS 84 horizontally and vertically. It would mean that all coordinates are in latitude and longitude, so in degrees, like on a GPS. It works. It's not super practical if you want to start measuring out surfaces, etc. But then you could just switch to the UTM zones and you get a so-called projected coordinate system, which means your numbers are in Cartesian, on a Cartesian scale. So X and Y are proper numbers and not degrees anymore. Or you just ask a local surveyor or GIS person what they usually set it up to. They often don't know why they're using a certain system either, but just somehow it established in one way, and then it's best to stick to what they are using. Or then ask for that EPSG code and the the site, spatialreference.org, and there is another one too, is in the notes of these slides. Cool. Any questions on coordinate systems or anything we just discussed now? If not, then it's 2 o'clock and time for a break. What do we do? 10 minutes, 5 minutes? 10 minutes, I think should be fine. Yeah. Then I think we can continue. Still sharing my slides here. And I hope the break was good for you. It was a lot of information and we'll have quite a bit more to work through. After this last hour, you should now have a better idea of what a spatial analysis is or what the word means. GIS, raster data, vector data, resolution, map scale, and coordinates. In this next hour, we will now dive deeper into remote sensing technologies, more specifically the different types of imagery and what they can tell us or what they're used for. And since this learning journey is about gravitational hazards or flooding and their risks, we'll explore our options regarding modeling the relief a bit closer as well. So what we call an aerial image so far is a so-called orthophotograph, or simply orthophoto, or also orthomosaic at the time. It is a geo-referenced aerial or satellite image corrected to eliminate perspective and geometric distortions, resulting in a true scale image that can be used as a map. Orthophotos are created by combining aerial or satellite imagery with precise elevation data, such as digital elevation models or terrain models, to correct for distortions caused by the camera sensors and their viewing angle and the terrain relief. Raw imagery from satellites or aircrafts or even from drones will always be distorted due to just the way the camera is and the way the surface of the Earth behaves. So you would not be able to measure exactly from an unprocessed image. Then the electromagnetic spectrum. The orthophoto we just seen on the previous slide was easily recognizable to our eyes. We recognized roads, buildings, vegetated areas, etc. Since it was captured with a sensor or a camera that records the incoming light in red, green, and blue, which is the visible light or the colors our eyes perceive, which is 400 to 700 nanometers on the electromagnetic spectrum, and those are the wavelengths, basically. Some sensors can capture data, for example, in the near infrared area, or even further down the electromagnetic spectrum, or either the other way. We didn't start at 0 here. Each object on Earth that is hit by light absorbs, emits, or reflects light in a specific pattern across this spectrum. Depending on the object's characteristic, it returns light in some areas of the spectrum stronger than in others, and each object therefore has its very own spectral signature. For example, we see here those lines. Water, the blue line, reflects strongly in the blue part here of the visible part of the spectrum. Hence, this is exactly why we humans perceive water as blue. Vegetation, of course, with a decent reflection in green here. That, oh, can I find myself? Yeah, here. In green, so we see it as green if it's healthy, but it has an even stronger output here in the near and a bit also in the shortwave infrared. And we will get to that in the next slide as well. Or then the brown line, will be soil. It reflects green, blue, and red almost equally. And that's our eyes naturally make basically a mix, and that's why we perceive it as brown. If data is captured with sensors sensitive to wavelengths of different parts of the spectrum, we will first have to process that data into something we can recognize. We still have to bring it back to this area here so we humans can see or recognize something. So we need to assign it a color of our liking, depending on the numeric value to visualize it. Some sensors just have one or two or more areas than the RGB sensor, which are then called multispectral sensors. So you can see here, second line, could be that the sensor has is sensitive to blue, green, red, and near infrared. So for channels, or often also called bands, and that would make it a multispectral image. Some sensors are sensitive to thousands of different wavelengths, and those are so-called hyperspectral sensors. That would be here at the bottom one. This one is still something, yeah, it's being done, but it's hard to work with because there's just so much data around, and to decodify it, etc. This is hard to do, so it has not become a very useful tool yet. But I'm sure with where we are going in technology, it will pick up more and more. And of course, there are the thermal sensors. So you see this purple arrow here, which concentrate on the return of heat signals, also part of the infrared section, just a bit further down. We'll talk about those a bit more in detail as well. So a multispectral image captures wavelengths in more than just red, green, and blue, or for example, the near infrared as we just saw. That vegetation has a high return in that part of the near infrared spectrum, so here. And this is mainly due to the amount of chlorophyll in the plant. The more chlorophyll a plant has, the healthier the plant is, the higher its return in the near infrared section. Hence, this type of data is used in forestry, agriculture, and land cover mapping. It allows us humans to better understand the state of the vegetation. We can even calculate an so-called normalized difference vegetation index. No need to remember the word, but you may have heard it already. But what it basically does, and this is a simplified formula here, but it's just taking the high values here and subtracting the low values in red, because the plants absorb the red light, and the bigger the value, right, the bigger that difference, the healthier the plant. So this is a nice way to then visualize this data. This we can see here on the right at the top, there's an RGB, so normal colored image, and at the bottom an NDVI image, which tells us, yeah, we can see the lines of the tractor where the vegetation is either squished or there's just soil. We see that those are red areas, so there is less. Well, we don't have the scale here, which is bad, of course, but I'll explain it. There's just less vegetation, so less chlorophyll, less return in the near infrared area. And for thermal imagery, the sensor senses between 1 micrometer and 14 micrometers on the spectrum. So we heard before, the visible light is between 400 and 700 nanometers. So here we're talking about much longer wavelengths. And this type of sensor are used to observe or to do heat loss studies of buildings, or do search and rescue missions to find humans or animals, but also, for example, in agriculture, because plants with closed stomatas, so they're not releasing any water vapor, and tends to become hotter. And plants close their stomatas should there not be enough water. And this means we can detect water stress, hopefully sooner than that the plant visually or shows it on a normal image to us. Satellite data can be used to create many useful outputs and information, especially if combining camera data, radar data, and laser data. Then outputs like the following can be built, like a radar satellite imagery. We didn't talk specifically about radar, but radar is basically radio detection and ranging. It sends out radio waves and looks how they are being returned. And that can give us an image that is texturized, and usually it's this type of look here, black, white, grayish, which will indicate, if something is smooth or if there is something that reflects those radio waves in a certain way, or in a jagged way, if you want to say so. Then seepage detection, for example, for oil spills, we have another one there, oil spill detection and monitoring that is widely done by many nations. Because oil on the surface of the water, it forms a film that is like a mirror. So the radio waves are reflected directly out. There is no return from that area, so built black holes, and that can easily be seen or visualized in the data that we are recovering from these analyses. Then we can do geological mapping, and of course can use that data also to create elevation data. With this, we come to the next topic, where we'll be talking about elevation models. I think this is important to talk a bit about, where it's not directly satellite related anymore, and there are many different ways we can create elevation models, but here in the learning journey where it's about flood mapping or gravitational events, it's interesting to understand what elevation models are for and what types there are, etc. Elevation models model the relief change of the Earth's surface. There are different ways to collect the data for these types of models, either by satellite, radar data, aerial imagery from drones or aircraft, and applied photogrammetry, which is something we'll talk about in my next session, the fourth, or then using LiDAR sensors, where LiDAR is also light detection and ranging, and similar to radar data. Or then there is another option, and that's humans walking a GNSS receiver and actually registering or recording elevations of single points, and then entering these into a GIS system and just interpolating them or creating control lines from those. As you can see here, there are different types. You may have seen the words DTM, DEM, and DSM. DTM means digital terrain model, and DEM digital elevation model. There's no clear difference between the two, respectively. It's all often mixed, but basically you just need to remember that DTM and DM are not DSMs, where the DSM is a digital surface model that contains basically all the objects and buildings that often man-made, or then it's vegetation, and they are included. So you would get the blue line will be visible in your software. Like here on the right, we see a digital elevation model that looks very irregular. This usually means there is some forest or other stuff on top of the surface that is still in it. So you're not getting the bare ground information. Where with the digital elevation model and terrain model, oftentimes it's meant that you get the surface or the elevation of the ground without any objects on top. So if there is forest, the forest would be like cut out, and then only what the ground level exactly is what you're interested in. it's totally, I mean, it's important to know that there are these two different types of data of elevation, just so you understand what you're getting. Depending on the application you're looking for example, flood modeling, it might be interesting to have the trees and the buildings in it to then simulate how far the water climbs up towards a building, etc., or do other types of modeling where one could even look at turbulences the water creates at the edges of the buildings, etc. And of course, what we're, for example, in terms of gravitational events, we're specifically interested in the steepness. Since elevation models portray the relief of the Earth's surface, it can also tell us where it is steeper or flatter. One can calculate the slope and visualize it on a map with this type of information. The input is an elevation raster, like here on the left. And then each cell has a location and a height value. Then the algorithm for calculating the slope extracts the steepness of the slopes, and ultimately those new values can be categorized and colored, like here on the right, to show us the incline of each part of the terrain. And then another way to elevation is visualized on maps is through contour lines. Contour lines give an idea of relief in topographic maps. There are lines that join points with the same height with regard to level 0 reference. So that's picture number 8. In most cases, these lines then represent the intersection between the relief and horizontal planes that are equidistant to the reference level. So here in image C, you can see those horizontal planes that sort of cut through the terrain. And we see also that it's a bit small, but 0, 25, 50, 75, 100. There's always 25 meters between each of these horizontal planes. So we would get a contour line every 25 meters. And that's called equidistant. Then when each of these lines are projected on a plane of the drawing, it constitutes the basis of the topographic map, like here on H. And this representation obviously requires selecting a determinate number of planes according to the accuracy wanted, and especially the scale of the map. We need more contour lines if we need more information, and less if we need less information. Since the distance between a line and the next one is always the same in reality, so the 25 meters, their projection on a map will give an idea of the relief. If contour lines are very close, like on a cliff or a coastline, they indicate a steep relief, which is also the case here on this drawing on the left. If there are spaced, they indicate a smoother relief, so it's flatter. You must remember that the height difference between successive lines is always the same, okay? Always those 25 meters in our example now. And that is the reason why all topographic maps show relief with lines that always have a value multiple of a number known as equidistance. And here on the left, you see a model the terrain. And if we would bring this onto a projected planar drawing with contour lines, it would look like this. We go back. So we have the 3 hills. And then we see here how the contour lines sort of, well, converge is maybe the wrong word, but build smaller and smaller circles where those 3 hills are. Okay. And for this, we have a small little exercise again, where Nora will put us into groups. But before I share the link in the chat, and please click it before you end up in those groups. Yeah, that's the right one. And the task is to match up the contour line drawings at the bottom with the landform shapes you see at the top. So you find out which one's the volcano, which one has the lake, etc. Okay. If everyone is back, and we quickly discuss the results. I've seen this was not too hard for most of you. Some groups took a little bit longer than others, but I think most of you figured it out quite quickly. So, of course, here the crater of the volcano corresponds to the third image here on my example. Then we have here the contour lines that clearly have a big white empty space in the middle. That will be the lake. And then the two here were a bit more difficult, where one could well, maybe a bit small, but one could recognize that there's a canyon here. So one would be looking for some very steep contour lines that feel like a channel, and that's what we clearly see here. So that will match up with this one. And then was just one left over. So one can go this way, or we can recognize here the bit of a mountain range, then a gap, a little lake, and another like little peak on the right, which one could recognize along here. This is clearly the top of the range. He goes down and then back up again. In the notes of this slide, you will also find the link to the site I have this example from. It's a game for people that do orienteering sports, and there are many more examples if you like this type of stuff or want to just practice a bit more. Any questions around contour lines? If not, then we'll continue. And I said we'll be talking a bit more about resources and costs of imagery. Maybe I should have put the word data, because not all of it is in imagery. Of course, we always make it look like an image, be it RGB or some colors that give us information. But in general, we have the options to go to get that data either from satellites, aircrafts, or drones or unmanned aerial vehicles, where we're talking commercial ones and not military ones. On the satellite side, as already said at the start, there are the four companies: Maxar Technologies, Planet, UP42, Airbus Defence and Space, which provide the imagery or elevation data that they generated using LiDAR or other means. And it's a matter of either just doing a plain request and one gets an offer and one pays, or maybe your organization has already a deal with one of these companies, or those companies may be providing special terms and conditions to humanitarian organizations. It's just a matter of, there are not that many, so ultimately I believe all of them will already have some program in place. We can explore that further for you if you want to. Resolutions will be looking at the 30 centimeters or up to meters, and usually satellite data you get in a couple hundred square kilometers, so you really want to cover a big region like all of Switzerland or half of Switzerland or half of Africa if you want, etc. Usually the larger the region, or if it goes towards the size of a continent, etc., it's just the amount of data becomes bigger and bigger. So you may decide to reduce the resolution at which you want to work with, and therefore you might see less details, but potentially to do a general overview of the elevation or where flooding most likely happens, could be done at that type of level. As we said already, a couple $100 probably per square kilometers or even less are possible for satellite imagery, where you need to keep in mind that there are different ways of ordering them. You can get it, you can say, I need it immediately, I need it tomorrow or in 2 or 3 days, and they will do their best to have a cloud-free image for you if it's camera collected information. Radar can go through cloud, so there you would be safe. But yeah, you ultimately pay more for short notice orders. You can pre-order to get it in a couple months. And you can also take data from the archive, of course, which tends to be cheaper. It's older, but if you're looking at an area that hasn't seen any change in the last 2-3 years, but is still prone to some hazards, you might be fine totally with 3, 4, 5-year-old data that you could get from their archive. Then aircraft imagery, you would have in the region that you're interested to get the imagery from, you would be looking for a so-called aerial survey company. I say it's best to look for a company that is based in that region because the transfers of planes, the whole import, export of equipment and so on, it takes time and money. So it makes it ultimately more expensive if the aerial survey company has to come from far away. You can get resolutions around 5 centimeters to 25 centimeters per pixel. And we're talking around, it really depends on the type of equipment they're flying and if they really want a job or not. You could pay anything between $200 to $600 per square kilometers. And organization time often takes a bit longer. That said, it totally depends on the season. If you've been in Switzerland the last 2 months, you know that there would have been no chance to do any aerial survey whatsoever because the weather was just not very nice. And then depending, well, if there are country changes, etc., there may be regulatory things that need to be clarified up front, which also take time. If we're going to drones and UAV, you can either outsource it and find a UAV mapping company in the region you need the data from, or you have your own drone, and actually it's rather simple to fly a smaller drone and to use applications on a smartphone or on the controller that come with the drone to fly smaller areas in a way that one has enough overlap and can generate overlap between the images, which we'll talk about next week, and which will then help you to produce the data. If you do it on your own, the downside of the UAV data is that you'd have to process it yourself. If it's a lot of data, you need a very strong computer and good software to do those calculations. This is usually called photogrammetry software. We'll look at them next time. But they're either a separate module of those GIS software that we mentioned today, or then are entirely separate softwares. In terms of resolution, we'd be at around 1.5 to 6 centimeters per pixel. It can be very cheap, 25 to $100 per square kilometers. However, one drone can maybe fly half a kilometer in one flight or even less. So then it's more time effort that counts than the actual square kilometers. So you might take a couple of weeks to collect all the data and another couple of weeks to process all the data. That said, 500 hectares in one flight, Well, that depends also on the country you're flying in, because there are lots of regulations around flying a drone, which could hinder the drone or the operator to actually fly this size of area if he has to stay within so-called visual line of sight. So if the operator always has to be able to see the drone, he ultimately cannot go that far. So you see, there are all these different advantages and disadvantages to these types of data. And I guess it makes it a bit harder at times to select the right solution for the right project. But throughout the next sessions, we'll definitely look more into that, and definitely the size of the area you're looking at is a big point to consider, and then the time you have to collect it, the money you have to acquire it, etc. So we'll be digging more into that. Any questions about this slide? And we have sort of one more to go, and I didn't want to.
I raised my hand, but you didn't see
sorry, I didn't see.
Just is there, as we have like QGIS, is there also satellite imagery for free? That can be used, and that can, that I can get as a customer in a way that it is useful for me. Already transformed data into the information that I need, to say it like that.
To which level? Well, yes, there is definitely, you can, many countries these days have some geo portal, either organized by the state or down to a smaller region, where when they have imagery available on a server, and you can just connect that type of server into your QGIS, and then it automatically downloads the data for you. That is possible. However, you oftentimes the metadata is not complete, so you will have to probably explore a bit from when the data is, like when has it been collected, or yeah, what resolution is it at? Most often they're actually not good enough.
Mhm.
Elevation data is most likely available at a good enough resolution, depending on how accurate you want your analysis to be. But we can make you guys a bit more of a summary sheet where we have those links available, at least the most common ones. ArcGIS from the company Esri, even if you don't have the license, they are providing data streams that you can they're available as a data source.
That would be helpful. Yes.
Mhm.
Yes. Thanks.
So the last type of GIS I wanted to introduce was the participatory GIS. Maybe some of you have heard of it or not. It combines a range of geospatial information management tools and methods such as sketch maps or self-made 3D models, like here in the image, or aerial photographs and GPS measurements. This particular example here is from the organization CTA, the Technical Center for Agriculture and Rural Cooperation. They did this in 6 or 7 places, and they measured that actually doing this type of participatory GIS really helped the local communities to better understand what everything is about, and to better grasp the point of why they should not be building houses somewhere, etc., or other types of spatial issues they may have. The link to this book or these documents is also in the notes of the slide. Well, and with this, I hope I was able to give you an overview of remote sensing and GIS, different types of data, and how they can be used as data sources and tools to work with that data to create required outputs. I know it's been a lot of theory. We covered all of this, but I felt like it's needed for the rest of the following sessions, and I hope to be more practical and get you to do more exercises and stuff to do yourself in at least my next session. I'm sure Georg will have some more exercises for you as well. Do you have any questions about any of the topics that we covered today? If not, I'll pass to Georg or Tony, I guess.
Yeah, to me. Thanks a lot, Andrea. Listen, don't feel bad if there were no questions. I was with 3 colleagues in the last group, and we were very quick, with this relief, because we also noted that, well, we're still analog guys and we know a bit this mapping stuff. But with regard to the basics, or, that the topics that you provided, that needs, at least from my side, and that I'm not a geographer, and probably all who are not geographers, they will need a bit of time to digest that. But I think it was very insightful. You provided what we need here, and also a bit the gaps that we have there as well, and where each of us, at least persons who are in the same situation like I am, I know there are others, who are much better versed, that we need to go through it again. But thanks a lot. No, you provided this, I would say, the basics there to continue, this art. And I'll, as always, it's a bit saying much if it's the second webinar, but I just pasted the link to the evaluation. So always before we come to an end, please get the link, and if you have time after this, just a little bit of time after that, we would be very grateful if you can fill it out and send it in. It's anonymous and it will not take much of your time, and it helps us for the organization of further learning events. So slowly coming to an end, or even more quickly, 5 minutes to the end. Let us have an outlook on the next webinar. And great that Georg is still with us, and also your laptop still has some juice. So please, can you tell us in a sentence or two about what we will have a look at the next webinar?
Sure, Tony, thank you. First of all, Andrea, thank you very much for this very interesting information. We can use those information in the next session, and if there is a need for some repetition, I'm sure you can help us, Andrea, with that. For the next session, do you remember we learned tools for hazard analysis, specifically for floods? In the next session, we will use those tools for different exercises that you will be able to use them for your daily business. Especially the peak flows, we would like to define them in practical exercises, and then to check out if this running water have enough room in the channel, in the river. And if not, outflows will occur, flooding will occur, then we have to define the flooding prone areas. This is the aim of the next session, to map, to define or create our hazard map. In some words, Tony, that will be the content of the next session. We'll be happy to meet you there.
Thanks a lot. During your presentation of the outlook, we had Michael or Nantenine, I don't know what your name is. You had your hands up and you put it in your chat, but please, use the mic if it works to raise. Okay, you don't have a mic. I see that. So I read it out loud. You talk about the DSM before on presentation. My question is there any open source website which provides this kind of data? And then many thanks for this great presentation. That's not the question, but that's an appreciation, but I also wanted to share that with you. So what was that, the digital service model or the DSM?
Oh,
okay.
Yeah. Well, there is elevation data available. It's not a surface model, but it's sort of a surface model, but it is at the latest SRTM, shuttle radio topographic mission data collection, is a 30 by 30 meter grid across the globe. And it contains pretty decent elevation data, but depending on the resolution you're looking for, that might not be quite enough. But it is for free, and I posted the link in the chat, and I'll put it in the slides as well.
Okay, great to put it in the slide. But anyone who want it, I just downloaded it and it looks great. Just click on it, and then you have it for sure. Okay, thanks a lot. I don't see any other hands raised. So from my side, that's it for today. I hope that you found this webinar as capturing as I have. And I have Georg who has, I wanted to take you out to mute you because I think you have you had some background noise. Sorry, Georg. And I'm looking forward to seeing you in 2 weeks' time. It's Wednesday, 26th of April, for the next webinar module, as Georg just provided the outlook. So bye for now and have a great day. And I would like to have Andrea just stay with us just for a minute or so later. So see you in 2 weeks' time.